Hello. So now we'll see some applications of Bernoulli's theorem to understand how to apply the Bernoulli's theorem. So one of the application of the Bernoulli's theorem is the Venturi meter. So there are two types of setup of Venturi meter, one which is applicable for liquid and another which is applicable for gases. So first we'll study for the liquid. So here this is a setup. This is a schematic diagram on which this works. In this case, there is a two cross-section areas we have seen, and one cross-section area is small one and one is bigger one. Here the velocity we have taken as V1, here the velocity we have taken as V2. There are two tubes going up which are open to the air, and the fluid will rise into them. And here the height is H1 of the liquid, and here the height is H2, and the difference in that is delta H. So let's first discuss why this setup is there, why this Venturi meter we use. I mean, it's the application part, but where we apply it and why we apply it. So you see, when we talk about the flow of fluid inside the pipe, it is very difficult to measure the flow, because when the flow is happening inside the pipe, nobody can see it. And we need to calculate, we need to know about that flow, because based upon the flow, there will be pressure inside. Because in case of Bernoulli, you must have seen the kinetic energy, which is half rho V square, and the pressure energy, which is P, they are dependent. So if there is any raise in the if the velocity is increasing, there will be changes in the pressure, and pressure goes for the forces. So for some range of velocity, the pressure might be in the range which might damage the pipe. So to prevent that condition, we have to measure the velocity. At the same time, we need to calculate the velocity at different locations so that we can measure the flow, how that is happening. So to measure the flow and to check for the failures, we have to calculate the velocities on V1 inside velocity V1 and V2 inside the pipe. We cannot open those pipes. So this Venturi meter help us there. It is an instrument by which we can calculate the velocities velocities of fluid inside the pipes without even opening them. Okay. So this is our Venturi meter, and this is based upon this Bernoulli's theorem. So let's see the application. Let's see the calculation and how we will get the formula for V1 and V2. Okay. So this is cross section area 1, A1, V1 and A2, V2, and the heights are there. Let's call it 1 and let's call it 2. This is my inlet and this is my outlet. This is my test volume. This system is my test volume. So at this point and that point, we'll try to apply things. So the first thing we want to apply is the continuity theorem. So if the flow is steady, if the flow is streamlined, we can apply the continuity theorem. So let's apply that. So from continuity theorem. So if you apply the continuity theorem, it becomes A1 V1, the value here, the volume going, the rate of flow, rate of volume which is going inside A1 V1 will become A2 V2. That's my one equation. And the thing is, majority of cases, areas will be known. You can measure the area without even opening the pipe. So in this equation, you see there are two variables, V1 and V2. So we need second equation so that we can calculate them, and second equation we get from Bernoulli's theorem. So what we will do, we'll apply the Bernoulli theorem at this and at that point. So it is a horizontal pipe. This variation, you can neglect that variation. So since this is a horizontal pipe, let's apply the Bernoulli's. For horizontal pipe. The equation is half rho V1 square plus P1 is half rho V2 square plus P2. This is the equation. And you see, since this is a horizontal pipe, the H1, rho Hg1, rho G H1 and the rho G H2 term, we neglect that term. That is equated and cancel it out. So let's put the values. So half rho V1 square. And then we have to write the value of P1. P1 is the pressure at this point. P1. The thing is, to calculate this pressure, we don't have any mean, but we have a mean. This P1, we can measure from the fluid statistics. So the P1 is equals to pressure at this point is equals to the pressure at this point plus rho G H1. Remember. So it becomes P ATM, atmospheric pressure, plus rho G H1. So in place of P1, I can write P ATM plus rho G H1, and that is equals to half rho P2 square plus P2. Similar basis, on the similar basis, this P2 I can measure from here. The P2 is the pressure at this point, At this point, the pressure is P2, and this P2 pressure I can measure from this. So here the pressure is P atm, and this height is rho g h2. So the P2, I can write it as P atm plus rho g h2. We put this value here, it becomes P atm plus rho g h2. You simplify this equation, P atm and P atm will cancel out. If you multiply it by 2, this half and half will cancel out. So if you rearrange this equation, the V1 square will be equals to V2 square plus 2G H2 minus H1. This is our equation 2. So basically this term you take it on this side, and the P atm and P atm cancelled out, and you divide it by density also. The density terms gets cancelled out. So now you are having two equations. One is this equation, the second is this equation. And in these two equations, you find two variables, V1 and V2. H1 and H2 these are things we calculate, we measure. H1 and H2 are measurable quantities. So what we will do, we will replace the value of V2 from the equation 1 into the equation 2. So from equation 1 and 2. From equation 1, we are putting the value of V2 in equation 2. So V1 square will be equals to, in place of V2 square, it will be A1 square upon A2 square into V1 square plus 2G H2 minus H1. So this value we will take on the left side. So V1 square 1 minus A1 square upon A2 square will be equals to 2G H2 minus H1. So we have to calculate V1. So what we will do, so this V1 will be equals to, we'll take it on that side and we'll take the under root. So V1 will be equals to 2G H2 minus H1, which is nothing but delta H, which we can measure, divided by 1 minus A1 square upon A2 square. This is the value of V1. So now you see H1 and H2 are the quantities which we can calculate, and A1, A2, that also we can measure. So this value of V1 we can put in the equation 1. So from equation 1, we put the value there. So the V2 we will get as 2G H2 minus H1 divided by 1 minus A1 square upon A2 square. Now you see, this V2 is A1 upon A2. So here, A1 upon A2. This is A2. So the V2, the value of V2 is this much, and the value of V1 is this much. So these are the values we calculated here. So in this formula, you see, if we want to do some approximations also, we can do them. Meaning in terms of approximation, sometimes what happens now, this A2 value is quite large in comparison to A1. Generally. So this principle we apply in case of water, like there is a drainage system, there is a water supply system. So when the water gets supplied, the original pipe from where the actual water is coming, the dimension of that pipe in comparison to the pipe at our home is very large. It's very large. So what they do, they calculate, at our home we have a fixed diameter of the pipe. So that value they know. And the A2 value is taken at the time of sending the water, like at the cleaning center. So that A1 upon A2 value, that ratio they already know. And they put an instrument, barometer, and from the barometer they keep measuring the value of delta H, and that delta H, from the use of that delta H, they can calculate how much flow is happening at your home. So that gives them the calculation to measure how much water you are using there to put the bill. So one more time, this Venturi meter. The purpose of the Venturi meter to measure the velocities for various reasons. We want to calculate the velocities inside the pipes. So this is our schematic diagram. This is not the actual diagram. This is the scheme of things. So there will be smaller pipe, there will be bigger pipes, and here we measure the height, or we can measure some. We can use some different method to measure the pressure. This system is there, this portion is there, so that we can calculate the pressure at this point, and this system is there so that we can calculate the pressure at this point. So here we first use the continuity theorem. Reason being, just to use the continuity theorem, all you need is the streamline flow, which is there always. So we use the continuity theorem, one equation we get, and then we put certain condition, because since in this system there is no pump, there is no external agent, and at the same time we have already assumed the steady flow is happening, so the flow, there is no viscous force also. So with the application of that Bernoulli's theorem, we get the second equation. This was our second equation. So with the use of these two equations, we calculated the value of V1 and V2 in terms of delta H and in terms of A1 upon A2 ratio. So this is the value. So this instrument we can use for the fluid, because if it is a fluid, it will not go out from here. We cannot use this instrument for the gases, because if I replace the fluid with the gases, these gases will go out through these pipes, because these pipes are open to atmosphere. So for the gases, we need separate system. Process will be same, but we need separate Venturi meter, which should be completely closed, not too open. That should not be open there. Okay, so that we'll study next. Thank you.